Scientists.
Yes, bright young scientists or bright young Africans. Okay? The
Right.
sentence that we use to write a lot. So here is the cohort of bright young Africans from Tanzania, Kenya, Zambia, Democratic Republic of the Congo, Nigeria, University of Maiduguri, Zambia, and somebody from Cote d'Ivoire.
From where?
Cote d'Ivoire.
Ah, Côte d'Ivoire.
Yes.
Bonjour, cher ami.
Bonjour, monsieur.
Okay.
So he's here.
Right.
You can say bonjour to him.
Yeah. On dit quoi?
Ça va bien. Et nous?
Ah, là, c'est bien. On va garder le contact après.
Ok, pas de souci.
Super.
S'il vous plaît. Okay, so we thought of running a short course on genomics and metagenomics, really hands-on. It's the first time we do this. So the idea for this first cohort was, first of all, for us to learn how to do it and to prove a concept it can be done. And then we will improve from this, making it more better and better. Our intention is to have it held regularly. And we have a branded group of trainers. We had Janos Kaweska from South Africa, Maki Royamam from London, myself from Tanzania, Ximana originally is from Rwanda, Mapunda from Tanzania, Gaspari Tanzania, Kinimi Tanzania, Chilaza Tanzania, Charles Tanzania. I'm sorry if I'm forgetting someone. You are coming to fertilize that group because you are originally from Benin, but now you are Danish.
I'm a Tanzania alumni.
Okay, also a Tanzanian alumni. Sana Sofonia. Yeah. The Tanzanian alumni also. College of Veterinary Medicine. Formerly, you were working with Corera, is it?
Yes.
And then transitioned for your PhD in Denmark, then got a postdoc, and then you are now associate professor there. So thank you very much for agreeing to our request and for you yourself offering to share some knowledge on what you have been doing. And now I invite you you'll start with a bit of your introduction and then give the lecture. I am involved in a proposal writing. We are developing a proposal to the pandemic fund. We were shortlisted, and today we are having a regional meeting with the FAO. Just started with Harare. And so I'll sneak out. I'll be listening on my phone, but then on my laptop, I'll be going on with the regional meeting for our application.
That's all right.
This is a $12 million application. So,
that is
billion-ish. Imagine we get that. We'll also get a share. We invite you for a training.
We'll get it. All right. So maybe I will. Yes, all right. Thank you, Prof. I'll just go ahead and share the screen and then take it from there. Also, that will include also my introduction. As Prof. Misinzo said, I'm Gildas. I'm from Benin, but I had a wonderful time in Tanzania, doing my master's there. And then later on, I got some position, PhD position in Denmark, and I went to University of Copenhagen to carry out my PhD studies. And back then I was working extensively on the genomics of cholera in the African Great Lakes region. So I'm still super attached to Tanzania, Kenya, Uganda, DRC, because I was working around the three major lakes. Lake Victoria, Lake Nyanza, and also Lake Tanganyika. So until recently. I think my last paper from that study came last year. So I'm sort of still working in that surrounding, and that was the paper in the emerging infectious diseases. So when I saw this information online from Professor Misinzo's Facebook, I couldn't resist. I just offered to, if I could get a minute to share information with you, that would be super good. So after the PhD, of course, I was about to go back home because I started working short term in my home university, which is University of Abomey-Calavi in Benin. But then the department wanted me back for a postdoc here, which I took, and then I finished that. That was last year. Then I went through some of this training as pedagogical. And there were some things to do, some exams to pass to get into a new position after the postdoc. So I got into sort of assistant professorship, So that's what I'm doing, and I'm extensively working on genomics and metagenomics and a bit of twist into machine learning. And I'm now kind of having my own research group slowly building up within the section that I'm in, because I'm now having 2 different fundings directly to myself, and we will talk about those during the presentation. So my talk today is, of course, about it really goes into what you guys have been doing. I've been monitoring Misinzo's page to see what is the exact program you're working on, and I've had also the template of your program, and I look into it, and this is what you guys are doing. I'm just bringing in a small taste of machine learning, how we could tap into this new aspect of analyzing genomic data. So I'm not going to teach you guys on pathogen genomics. You've been doing that for 2 weeks, and then some of you have been doing that already almost your entire graduate years. I hope you can hear me, right?
My name is Gildas.
Yes. Sorry?
Yes, hear you.
We can hear you clearly.
Super. All right. Thank you. Asante. So I'm not going to teach you anything about pathogen genomics and metagenomics. You guys already know that, and then you do it in many aspects, and we all know that, I mean, the outputs or the outcome of a genomic study is highly dependent on your research question or your hypothesis, whatever you're looking into. You ask yourself different questions. So I chose on purpose to put this slide here, but I'm not going to talk about it. What I'm more interested in today is how do we switch the bioinformatics side of it, because genomic has 2 sides. There's the wet lab where you do the sequencing, and then you have the dry lab where you do the analysis. Now the point is, how best can we do this dry lab in order not so that we don't have to be there all the time for all these analysis to continue to be run, and also to make better inference from it. So to start, I would like to have a very small interactive exercise with you. I know we only have 1 hour, but I would like to take the risk of wasting 10 minutes of it. And that is just to ask what you guys know about machine learning, whether you have heard of it before, or maybe some of you have been working in that field. Maybe you know a bit of data science, or you have been hearing about AI and the whole GPTs coming out now, both from OpenAI and all the others competitors who are bringing in ChatGPT and all the different GPTs coming. So maybe you have heard of machine learning also in a way. So I would like to just have an interactive exercise with you. So could you kindly take, whether it's your phone or your computer, I want you guys to just open, if you have a QR code reader, try to scan this code. If you don't have a QR code reader, you can just type in this very small link. It's tinyurl.com/AprilSUA. I try to make it small. I would kindly like to invite you on that page right now so we can have a very short exercise. So if you type in your browser tinyurl.com/AprilSUA, or you could just scan this page. It will bring you to a Padlet page. Let me see if I can open it. this is what you should land. I would just we don't have much time. If we can have a few people on this, then I will go ahead. So can you can you hear me?
Yes, can hear you.
Yes. So is anyone on the Padlet now? Have you landed here?
Yeah.
Either by scanning the QR code or by typing in your browser tinyurl.com/aprosua.
Yeah.
Right. So if we have at least one person per table, that is already enough to start. Okay. So we don't take too much time. But I just want to confirm. Do we have anybody at all who has managed to reach here? No? Should I go back?
Yes.
Right.
Yes.
Yes, okay. You can just scan the QR code from your screen, or you can just type in tinyurl.com/aprosua. I know it can take a bit of time, but it should be fine. We are not. I only have 14 slides, so it's fine. So, do we have a few people at least on the Padlets?
Yes.
Right. Super. Okay. So those who haven't managed, it's fine. Don't worry. You can join the others. So those who are here on the page, I just want to show you what we are going to do. The question, if I go back to the slide, the question was just to give your own reflection, like what do you think is machine learning, or what do you know about it, and just share your opinion on what you know. Okay, and this is how you do that. If you already know how to use a Padlet, you just go ahead and do it. Those who don't know, if you come on the page, bottom right, there is this plus button. Bottom right, there is a plus button. If you bring your cursor next to it, it turns into a pencil. Can you see that?
Yes.
Bottom right. Okay. Bring your cursor there. It turns into a pencil, and then all you have to do is on top here you can give it maybe your name if you choose to. You don't have to, but it's just I could do like this, and then I go down here and type my response. Okay. Blah blah blah. Machine learning is this. Blah 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 blah. Okay. And then when I finish, I'll just publish, and it should show up. Okay. So let's do that. Let's take just 2-3 minutes for everyone to quickly, those who managed to join the Padlet, to type in their opinions. Someone said it's about automating workflow. That is beautiful. So remember, when you click on the pencil, type in if you want your name. If you don't want, leave it, but just type your response. You could type it down here. It's I mean, it's very, very optional. It's just for us to have a reflection together. I would like to see those who have any experience at all with it, and those who would like to know more, or if anyone knows. Okay, so someone taps in metagenomics. So the question was, if I go back to the question, what you need to type in, write in the Padlet is just your opinion. The problem is that we are not in the same room. I'm online, so sometimes if I say people should open, okay, Prof has typed in something, and you could see the way he put it, right? So it's in the subject you put your name, and then down you can put your response. There's no correct answer here. It's all about, I want to know your opinion and what you know about it, and how do you think you could use it, whatever it is that comes into your mind. So Prof says machine learning is a customization of computing algorithm to run, I think, specific pipelines. The most advanced evolution in humanizing AI has been advanced by GPT-4. That is good. Really nice, Prof. Thank you so much. And then we will soon, in my next slide, see how we can distinguish between AI and machine learning, and also deep learning. And then we will see where do we land, where are we. Someone typed in, it's a learning contemporary subject by using sophisticated instruments. That is beautiful. Machine learning is about automating what is really happening in nature. Super. So, I mean, we don't have to sit here for long, but we can already see many people have very nice ideas. And Monica has actually even colored her post-its, which is really beautiful. So she's quite advanced on Padlet. So machine learning is application of computer technology to perform various activities, such as the use of digital applications to predict the weather. Beautiful. Gaspari, machine learning uses computer sciences to unlock patterns from big complex data. Super, that is actually even more accurate. No, not more accurate than the others, but just that is kind of reaching. Machine learning is teaching computers and then use the taught computers. For example, teaching a computer plant disease symptoms and then use it to tell farmers. Super. So this is a very good. Is someone asking a question? No.
No.
Maybe it's because of some interference. Okay. So I would like to leave the Padlet and go back to the slides, but you are welcome to continue typing here. It's going to be our discussion flow throughout the talk. Maybe I may not come back to it specifically. I hope I'm not missing anybody's answer, but I will see all of them later on. And if you want, we can still share that Padlet to do more interactive studies. Okay, so as you could see in many, maybe I go back here, in most of your reflections, in a way, you already know what it is and how it could be used. And I'll just tell you that machine learning is not actually that new. It's just that the wording has changed a bit, and there's a slight difference in the way we use it today, because we have all in the past done some statistics. Like a very, very simple exercise that we used to do, I remember in the masters with Professor Kimera, was like, you have the group of people who smoked and the group of people who didn't smoke. And then the outcome was those who develop lung cancer and those who don't. So you like to calculate the odds ratio. You remember stuff that when you smoke, what are the risks that you develop lung cancer in the future? So it's more like the same predicting exercise. The difference here is that you're training the model to learn that if you smoke, this is the amount of people who smoke, this is the amount of them that develop cancer. And these are some characteristics about them. You provide the model with enough data and enough information about each case and the outcome of that case, so that later on, the machine gets to learn a lot from your data, so that later when you give in a new data, the machine is able to tell automatically what is the likely answer. That's all. So the way it works, it has been used in many statistical inferences, but we want to see how best we could channel it into genomics, which is actually very much welcome into what you're doing. And I just chose to put this slide here to show, so we know what is AI. We know very much. I think a very good example that we live with on a daily basis is Siri and Alexa, or if you have a Netflix account, you always have these Netflix recommendations. It sees your behavior, the type of things you are likely into. If you watch this type of movie, then you get a new one. So this is AI overall. Machine learning is a portion of AI, which is mainly about training an algorithm, exactly as I said in the example, training an algorithm about a process, and then the algorithm being able later on to give you outcomes based on that answer. I even put some examples in the slide here, which I'm not going to present much. And then we have deep learning, which is a bit more advanced, but it's also an AI. Everything is within the artificial intelligence realm. And it's all about training your algorithms and the algorithm being able to go deeper. The difference between deep learning and machine learning is that deep learning is able to do this at multiple layer level, while when we are talking about machine learning, it's very restricted to what you have taught the machine, what you have taught the model. Maybe I should stop saying machine. But if you think you have taught the model that this is how this looks, if you say these are images of cats, and later on you bring in a tiger, the machine should be able to say, this may look like a cat, but it's not specifically a cat. That is all it is about. So if you teach your model that this pathogen or this sequence that I'm providing is African swine fever virus genotype 1 or 2, it should be able later on when you have a new sequence without having to go through a metagenomic pipeline, a bioinformatic pipeline, the machine should be able to spit out directly that this is this particular genotype of African swine fever. That is how you're going to train your models. And when you are talking machine learning, you have basically 3, but I think now it's like 5, but these are the traditional training machine learning options. You have supervised learning, unsupervised learning, and reinforced learning. The supervised learning is mostly the one we will do the most when we are doing genomics. It's more like you train it based on a specific data and variable, and the machine should be able to answer from a new data. But if you look into unsupervised learning, it's more like you let the machine do clustering. Like if you take that example with the cats, it should be able to categorize them for you. That is when you're doing unsupervised learning, and reinforced learning is more like when you teach a dog, okay, how to play a game, and then when the dog passes, like if you throw it a ball and the dog is able to catch the ball, you reward it, you say good. So it's like you are there interacting with the machine, and then when the dog fails, you punish it, and therefore based on that the dog learns best. So it's a bit of supervised learning, but it uses this aspect of a rewarding system. I'll give a quick example of what it is like in actual sense. This graph here is, let's suppose I want to take Kinimi as an example here. Let's say, can you hear me? Yeah, I'm just choosing Kinimi as a name here, that this is Kinimi's behavior when it comes to music, okay? Let's say Kinimi is more into high tempo music. So I put tempo on the axis and intensity of the music in the y-axis, right? So Kinimi is kind of a guy who likes music that the tempo is kind of fast, even though this is not true. I know Kinimi is a churchman. So he likes music that are kind of fast in tempo and also with very high intensity. So someone who is like into rock or something like that, okay? So the green are songs that Kinimi likes. So the higher the soaring and the faster the tempo, the more he likely he will like the more likely that he will like the song. And those that are more relaxed, let's say more like love songs, maybe Celine Dion type of songs, then Kinimi doesn't like that. Kinimi is not a romantic man. Right. So if we go, you know that it's very easy when there is a new song out there that is sort of relaxed and very light, automatically we know that Kinimi is not going to like that song. But when the song is into this category, for sure he's going to like it. Now what happens is when when there is a new song, this song I put here, song A, you have trained the machine on this first data here that this is how Kinimi behaves, and the machine knows. The day that you put in a new song, which is A out here, the machine should be able to categorize it. And it's very easily going to say, oh, this song is quite fast. When I look at the tempo as variable, and when I look at the intensity, it's also very soaring. So Kinimi is going to like it. So it turns green. But what happens when you have a song like this song B, which is almost, because when you look at the y-axis, it's kind of turning towards relax, and it's almost like middle of the intensity. So it becomes difficult to guess, right? You cannot tell for sure. Just by looking into it, it's difficult to say. So what a model will do is that it's going to use that B as a center and make a circle around it. If you have that circle around B, what happens is you realize that there is only one song that falls in the circle that Kinimi didn't like, but there is almost 3.5, or let's say 3, that falls within the same circle that Kinimi has liked in the past. So this gives the machine an idea that there is a higher likelihood that he might like this song, even though it is not to the extreme, but this is how machine learning comes in, and then this song will also become green. So now imagine a situation where you have more of this kind of data, quite a lot you cannot guess just by looking into it. So this is how you can use models to predict it. And then the kind of model you could use to do this, which uses this strategy is the k-nearest neighbor, algorithm, which is very good at doing this kind of analysis. But you have many other, like random forest is often the one you'll be using if you want to do genomic predictions. And of course, for the machine to be performant and be able to do that, you need more data. And that's what we have as a problem in Africa, right? Because sometimes we have a lot of data sitting, but we don't have a lot of data collected and analyzed. So the more data you have in your model, the better the model and the higher the accuracy. Because for the machine to be able to predict B accurately, it needs to have had quite a lot of data during the training process. So you have many different models of machine learning that you could use when you're doing genomic studies. Random forest is one, the vector, support vectors, and also decision trees. And I think you will also use neural networks quite a lot. We are not into statistics class, but it's mainly to show some of the models that you could use. I'm more conversant. I'm using a lot of random forest now in my new project. And I'm also using support vector machines. It all depends on what I'm looking into it to do. And these are not things you need. And the k-nearest neighbor I was talking about is this, and we don't often use it for genomic study, but I think maybe some other people do. Perhaps, I don't know. Of course, you don't have, it's not like you need to go and download the whole new software to do this. You can simply just run them from your Python pipeline or even R. And these two are open source features. So if you go in R, you can always install and load these libraries and run any of them on your data. You could also do the same with Python. Already from, if you want, you can do that from Miniconda already, if you want. For those who work a lot on Linux or OS terminals. So when we apply this to genomics, I don't want to take too long. Before I give you back, I don't like doing direct lectures. I always prefer something more interactive. But this is just the process. It's not that complicated. The usual process, which you always do, which is you have your isolates, whether it's a bacteria or a virus that you're working with, and you have done your nucleic acid extraction, and you run it here. I work more with bacteria. That's why it's looking like this, unless I'm working with metagenomic data, which is complex. You do your usual stuff. And after your usual stuff, then what you're going to feed into the machine is not the genomic data, is the output that you want to use to do your categorization. So let's suppose you're working with some bacteria, okay, which I'm more conversant with, and also some phages. And you want to classify by SNPs, single nucleotide polymorphisms. So when you reach this step and you've done your SNPs analysis, in the actual sense, you look at your tree or you look at your SNPs matrix, and you can say this strain and this strain are related, something like that. But in this case, you're feeding the model with the pairwise SNP data to train it so it can tell you which ones are closer to who. And that's the data that you use to train the machine. So you are not training the machine with the genomic data, but you're training it with the output of the genomic analysis. So it can be able to tell you who is the neighbor of who is a descendant of who directly. I would give, I have 3 case studies here. One that we have worked on and it's already out, and then there is 2 more that I'm right now implementing, both one project in Benin through this Canadian ITRC funding, and then one that I'm running here and in Vietnam. So this project was basically for the Danish, is specific to Denmark, okay? They wanted to know for 1 year, what were the main sources of salmonellosis in humans. So there have been some human salmonellosis cases. The idea was to know where were these coming from? What was the main source of the salmonella? So the main source so far, when you look into when you do the usual genomic study, they've realized that most of the salmonellosis or salmonella cases occurring in Denmark in 2020 were essentially coming from zoonotic sources, mainly from pigs, cattle, and all the other layers and other animals. So they were essentially coming from production animals. But how now can we predict which strain comes from which source is what we call source attribution exercise. So you can easily know how much has poultry contributed to salmonellosis, to human salmonellosis in the year. Or let's say in Tanzania today, how much is a pig production an issue into human salmonellosis? How much is poultry the issue? How much is cattle the issue? So that we can know where to put the intervention, the best intervention. So you go for the low-hanging fruit. You don't have to just do a blind intervention. You know more specifically, okay, in Tanzania today, maybe layers are the main source of salmonella to human. Then you know we go to layers. So this is the exercise to do source attribution of Salmonella typhimurium. The exercise, after you running the genomic study here using CGMLST, then you feed the CGMLST data into the machine to train the machine. So what you're telling the machine is, you're telling the machine that this isolate here, number one, or isolate A, is from poultry. And this is how it looks when you look at it compared to the human isolates. This isolate B is from turkey. This is how the CGMLST is compared to human isolates. This isolate C is from pig. And this is how the CGMLST looks compared to the human isolates. And so on and so forth. And you put in as much human isolates and as much animal isolates. So the machine is, the model is trained on a data where it knows specifically that these isolates or isolates with this particular pattern of CGMLST compared to the human isolates are from poultry. These ones are specifically from pig, and these ones are specifically from cattle. So later on, when you want to test the validity of the machine now, you bring in a complete new isolates, different from the ones you have used to train it. So you bring in maybe a pig isolates from a new batch, and the machine should be able to tell you the likelihood that this particular one is from pig. If you bring a new isolate from poultry, it should be able to tell this is the likelihood. So this is a very good example of the output where to the x-axis here, you have a lot of the human isolates. And up here, in the y-axis is the probability that it is coming from the particular source that you have up here. So if you take this human isolate here, this isolate up to number 10, the one up to 10, these 10 samples here, and then you go up, there is this much chance. This is the probability up to 1. So there is at least 90% chance that these isolates are actually, these human isolates are of pig origin. And then the color, like if we take the blue, so if you look here, these isolates from 16 to 19, which are human isolates, have this much chance that they are coming, 70% chance that they are coming from pig, but they have this almost 3% chance that they are coming from poultry. So maybe this may not be a good representation, but this is the output of one way of displaying an output of machine learning results. And then you can confirm this by going back to your genomic, the old way of running relatedness, which is the tree that you have here as a gold standard compared to what the machine is telling you. So when you are sure of the machine performing well in the future, you don't have to be there anymore for the machine to work. So you only need to bring in new data, and it will tell you how much chance it is there that this isolate you're bringing in is from this particular source. So that was an example of source attribution. This is a new project I'm having now. It's on Vibrio vulnificus. Those who know me, how I started with Vibrio cholerae, and I love working on cholera, and now I've moved a bit into other Vibrios, and one of them is vulnificus. And I'm having 2 different fundings on this one. One is from ESMIN, and this is from DFF. Quite okay money. It's a pathogen that is not an issue in our areas, because you guys in Tanzania, you have the Indian Ocean. In West Africa, we have the Atlantic Ocean, and I think these 2 oceans have quite high level of salinity. Vibrio vulnificus thrives best in a more brackish sea. It doesn't do well when it's fresh water. It doesn't do well when it's super salty. So it's very good with brackish water. So here in Denmark, it's the Baltic Sea. So Vibrio thrives very well in the brackish sea because the Baltic Sea is more brackish compared to the Indian and Atlantic Ocean. And the other thing is, it works. It thrives also best in the summertime when it's warm. In Africa, it's warm all the time though. But here, it's cold like 70% of the time. But from June onwards up to August, the sea surface temperature rises because, of course, of the ambient temperature that also rises in the summer. Now, what happens is when the temperature goes up and the sea becomes warmer, these kind of bacteria start to grow better. And as they grow, then people are more at risk of contracting these kind of infections. And Vibrio vulnificus is very, very opportunistic, but at the same time, very dangerous when it manages to catch you. And this is a very good amputation, or bad amputation, I would say. So it causes amputation when you have a wound infection, you don't attend to it, progresses very quick. And it also causes septicemia with the same fatality rate as Ebola. If you get the septicemia case, then it becomes the case fatality rate is almost 50%, which is very bad. But the problem we're having with vulnificus is we cannot tell which environmental strain is able to cause human infection. So if you take Vibrio vulnificus from the sea today, you isolate Vibrio vulnificus from the sea, you cannot tell whether this is able to cause infection or not, simply because the environmental isolate and the clinical isolate all have the same genomic content, more or less. And if you look into the expression, you do a transcriptomic study, you're seeing sort of the same level of expressions. What this project is trying to do is to be able to predict which strain from the environment is able to cause disease. And to be able to do that, it's not just the pathogen that comes in account when you want to account for disease severity. There is also the host factors. So it's more likely to occur in males than females, and it's more likely to occur in people with some uncompromised, with some immune issues, like people with liver diseases or people suffering with diabetes. And it's also more likely to occur in the more elderly populations, people with 60 years old and above. I have one paper out in March, already on the epidemiological side of this in emerging infectious disease. So what I'm feeding into my model now, which is the work I'm doing these days, I'm feeding into it the virulence factors data from the pathogen. I'm putting in the patient's health data and demographic data. So I'm telling the model, this is how the strain looks like genetically. This is the patient. The patient used to have liver disease, or is having liver disease. The patient is a male or female, and this is the infection outcome. So when you see these characteristics, this is how the disease turns out. So I'm putting in as much data as possible for the model to see what is happening, that when you have this particular strain with these virulence factors, and that the patient is having some conditions, and that the patient is of particular gender, and that the patient has this particular age, this is what we have noticed, that the patient had a severe case and had to be treated, or ended up being amputated or dead. So that later on, we are still at the training stage of the machine. So later, when I now have a new sample, and I put in the sample, the genomic data of the sample, together with the information from the patient, the machine will tell me automatically that this patient is likely to develop a severe case or not likely to develop a severe case. This is how useful you can use the models. The other way is we're also training the model with more environmental data in order to do what we already know as outbreak prediction, which is putting in environmental variabilities, meteorological data, and the machine will be able to tell whether there will be an outbreak. So this is more classic thing where we all know what we call predictive modeling, but this one up here is the more advanced part of it. The case 3 that I'll take is the Vietnamese project, which is funded by the JPI AMR. And it's a consortium, and I'm the PI from the Danish side in our consortium. What I'm doing on my part, on my work package in this project is I'm doing metagenomic analysis of hospital wastewater from Vietnam. So I'm taking wastewater samples, you run metagenomic analysis, and then what I'm showing here is just a picture. You don't have to mind that. But what you do, what you usually get after running metagenomic analysis is you have a profile, right? You know, this is the metagenomic profile of this hospital. And these are the factors. You need a lot of metadata behind it. So we know what are the drivers for AMR genes being present in that wastewater. You need to know the treatment systems in place, and then you need this sample over time. So I'm not doing machine learning yet in this project. I'm still doing the metagenomic part, which is the normal stuff that you do. You take samples, you run, and with nanopore now, you can actually do very good binding because you get longer reads and you're able to actually reconstruct pseudogenomes from the metagenome much easily during the binding process. So after this process, I'm going to be able to do the profiling for each sample based on where they come from. So what goes into the machine in this case is the machine will learn that when you take a sample from a hospital with this particular system of treatment in place, this is how the inlet wastewater profile look like. This is how the outlet looks like. And that is the metagenomic output that you're giving it. Then later, when you train it on this match sample, and of course, as I said, you need a lot of data all the time to train machines. Then the idea is that we don't have to be there all the time to be doing the metagenomic analysis. So that later, when you have a new sample and you run your pipeline, you get the output, you put it into your model. The model is be able to tell you that this particular sample, what are the to predict how much is it likely that this sample contains some AMR genes bioavailable and some resistant bacteria bioavailable, and you can be able to target interventions much specifically. The other part of the work, which is the viral part, is from the very same samples over time sampling. In the profile, this time I'm not profiling based on resistant gene, but I'm profiling based on viral pandemic threats. So just any viral copies in the metagenome, I'm doing a Shannon abundance test. And then you feed the machine with this information that when, let's say from January to December, according to some specific variations, this is how the profile looks like. This is the trend in viral presence, okay, in the samples. So later on, when you have a fresh sample that comes in at a particular time of the year with particular temperatures, the machine should tell you that there is a likelihood that this virus is emerging in the area and might spread, or that it's a completely new virus. It has not been there before because the machine could not see it in the cargo that you have supplied. So it's a new one. Or maybe it's not new. It has been there, but based on the trend, it's kind of rising and it could cause a disease soon in the human population. So these are other ways you could use your metagenomic or genomic data to feed into your machines in order to make more kind of proactive, because if I remember what I saw on Professor Misinzo's profile, it's outsmarting pathogens. So to be able to outsmart them, we need to be more and more proactive to take decisions. We don't always have to wait for the outbreaks to occur before we go take the samples and do retrospective analysis. We need to be more proactive now, so that already from the surveillance, if you look at the surveillance data and you train, I know Tanzania, you have a lot of surveillance data, even though it's obsolete, but you can train machine models on this data, and the model will be able to learn. Later, when you have a new sample, even before there is an epidemic peak, you can already detect this. Or when there is an epidemic peak, you take the sample, you bring it back into the machine will tell you already almost everything about it based on what you have trained the machine on. So a quick take-home message is that this has a potential for us in Africa. We haven't been using it much, The only project in which I'm trying to incorporate this in Benin is the project I'm having with the IDRC on waterborne diseases in Benin, looking into climate change adaptation. And I hope we'll be able to come up with something interesting for the government, because we got this together with people who are working in the ministries, even though I'm the coordinator. So we still have some issues, of course, issues with data, and you could see this is big data. You need a lot to train the machine on, quite a lot of data for the machine to be very accurate for you. And we can use it on many issues. One of the other challenges we are having is the issue with brain drain. We always talk about this, and the reason I like Tanzanian guys I've met in Denmark is they always go home. They always go home. Not always, but most of them end up going home, which is really beautiful. We don't have that culture from the west sides of the continent. We tend to stay abroad when we have the chance, the slightest chance to leave, we tend to stay. And that's why I'm trying my best with that. Every project I'm running, everything I'm doing is kind of related to home. So, and that's why I'm very happy, and that every year I'm home almost twice a year doing new projects at home and teaching from the university, even though sometimes I'm teaching online, having new master students and new PhD students coming here, going back to Benin. That's how I think I could be able to help. Even though for now I'm still mostly here, most of my time, but I'm trying my best to transition back slowly. And that's, again, one of the issues, because we have a lot of people who know how to do this analysis. As you could see in your classroom, there many of you are now very good with pathogen genomics, and some will be even better after the course. But the problem is that mostly when we get a better job outside, we leave and we don't go back. So just the take-home message is, let's try and see how best we can look into the future with this and improve public health decision-making using the genomic data combined with all these data sciences. And to be able to do this, of course, you need to be able and open to collaborate. And I guess this training is all about One Health. So there's no way you can do One Health without collaboration. So thank you very much for listening to my talk. I didn't make it that much interactive later on. It started very interactively, but then it became a one-man show. But I think it's 1 hour. We can't do too much more than that. I'm open for your questions and collaborations and everything. Thank you very much. Asanteni sana.
Okay, thank you very much, Gildas, for your nice talk.
Thank you, Jean.
Yes. So the talk is open for questions.
Yeah, for everything.
Yeah. So if you have
Yes.
question, comments.
Yeah.
Yes, Dr. Mwanyika.
Yes, thank you very much, Dr. Gil, for your
Right.
presentation. I'm very happy that you are doing a lot of machine learning predictive models to try to solve a number of challenges or public problems. So my comment is just, in our African universities, issues of machine learning and data science is like we are not having these disciplines in most of our universities. So you can find out we have a lot of problems, but we don't have the skills and technologies to play around. Only a few Africans have the opportunity to go abroad and possibly go there and work for the European problems. So I see there is a little gap that we as African, we need to invest on the machine learning data science as the Americans and the other continent do. So that's what I can say, that we have a gap in investing on the data science yeah.
Thank you so much, Mugu. I just wanted to answer you with some resources. You know, I'm trained initially in Benin as animal scientist. Then I moved to Tanzania. I started working in public health and food safety, and then I took some courses with Professor Kasanga, and I started doing pathogen, genomics, and evolution. So I started developing what I wanted to know versus what I was meant to learn. So I started moving into the direction that I wanted to. Then my PhD was essentially microbial genomics here, and slowly I started moving in that direction. But what I wanted to say is 70% or 80% of what I'm doing today didn't come from my training. These are things that came from self-learning. And one of my lovely things is Coursera and YouTube. I'm telling you, in Africa, we have the mind, we have the possibility. What do I want to show? If you go online, all you need is some internet. If you go on Coursera, you have a lot of courses on machine learning, you have a lot of courses on bioinformatics, and a lot of courses on genomics. Same on YouTube. So you might say maybe some Coursera courses requires you to register, but at least they allow you to attend the course, even though they don't give you at the end the certificates if you don't pay. But you don't need the certificates, right? So all you need is the skill. You can learn that. You can go online and learn. You can also go on YouTube and do a lot of self-training on whether it's genomics, bioinformatics, metagenomics analysis, Python programming, whatever it is, you can have access to that today. So you can even graduate from Oxford or from Harvard just by being in your room. So I would like to encourage everyone to do what they can do from their position, because as he said, the means are not there. We don't have the formal training offered to us, and we always sometimes think we need to go abroad, which is also true, but sometimes you don't have to. Even though I was here doing my PhD back then in 2016 to 19, I finished in 2019, but my supervisor was a very good guy in epidemiology, but he's not a genomic guy. So I told him I needed a co-supervisor. So I had to go to the other university, which is DTU, the Technical University, to find one nerdy guy who is very good. He doesn't know anything about biology, but he's a computational biologist. So he became my co-supervisor, and I would go and spend one day in his lab every 2 weeks. So sometimes you need to scavenge on your own if you know what you want to achieve. It's just my idea of the way I see this thing.
Okay, thank you very much. Another question, comment?
Yes.
This one.
Yes, Dr. Kinimi. Yes, can move closer here.
Professor.
Yes, hi, my friend Gildas.
You know, we used to call Kinimi professor since he was meant to be a professor.
Yes.
So,
Thank you.
yeah.
Thank you, Gildas.
Yes.
For a very informative presentation.
Thank you.
This is a new avenue in research using machine learning. To me, is the new area that we needed to explore. The question that I have is that can we predict the outbreaks using this machine learning if we have enough data?
Okay. Is that the question, or you have a follow-up question?
That's one.
Okay. Machine learning, I mean, I think since epidemiology was born, people have been able to predict outbreaks in some way. Sometimes it fails. I think, you know, there is this very good quote I love from Professor Kimera. He always says, all models are wrong, but some can be useful. And I love that quotation very much because it's very true. Even models that we used to use back then, like linear regression or Poisson regression, whatever it is, they are in a way able to predict outbreaks. But now with machine learning, which is a bit more improved, you are able to predict outbreaks. But again, predicting an outbreak is somehow a very difficult job to do because there is biology involved at some point. And you cannot just, biology is not maths. You can use the math as much as you can, but you need a lot of biological data. The good point, again, as I said, with machine learning, it's not doing simulation. What we used to do simulation, this is not doing simulation. This is using actual data. So you are feeding to it actual data, saying in every year, in this season, we have had this match people with this match animals with Rift Valley fever. And this is the incidence this year, this is the incidence the next year. And you're feeding into it maybe up to 10 years of data. In a way, the machine is not doing anything that your grandpa is unable to do, because your grandpa is also able to tell you that next year by this time it will be raining. And that will be more or less accurate, plus or minus some errors. And that is what the machine is also going to be able to do. So you'll be able to predict outbreaks. Of course, you have to leave some error margins, of course.
Yeah. Okay, thank you very much.
Welcome, Zay.
Yeah.
And then my point is, I really wanted you guys to not just look into machine learning as what we are seeing online today with the OpenAI products like ChatGPT, or don't look at it as just a predictive model, but more, how can it benefit you guys into genomic analysis? Like post-winning the area. We know pigs, after winning them, they always develop the area. So if you are able to have a metagenomic picture, a metagenomic profile of the gut microbiome of the piglets that developed the area over the past 5 years, for example, you have shown the machine, you have trained your model that every piglet after winning that had developed the area, this is how the microbiome was looking like. This model should be able to tell you in the future when you have a new piglet, based on the microbiome composition of that piglet, it should be able to say, this piglet is likely to develop the area after you win it. So that you know in advance that after winning, this pig is going to develop the area, so you are aware in advance and you take your measures. So this is another example of a project.
Okay, thank you very much, Gildas. Now, let's welcome Dr. Gildas.
Yes, thank you very much for your presentation, which is really great. Actually, the last part of your talk somehow has answered my question. So my interest was on the machine learning, because you need to integrate several variables so that you can have a better prediction. So I was trying to figure out, at some point you mentioned that you take the health of the individual, the environment and the like. So my question was about the gut microbiome, because I know that has a significant influence to the health of the individual, even maybe the performance of some of the drugs. So is there a model whereby probably you have involved the gut metagenomics as an input to the variables for the machine learning? And how it works, for instance?
Like if I go back again to what I was saying right before you spoke, this project is called Safe Pig Production, where what we are looking into is, you know, the pig production has one big hurdle, is that during the weaning there will always be that diarrhea coming up due to many mostly change of eating, because the pig move from having milk to start eating food. So when you take the gut microbiome, you run metagenomic profile of it. I mean, you go through the usual pipeline, okay, until you get your final profile, which is the diversity and abundance. Mainly, that's what we always want to look into the most. And later you can go down doing metagenomic assemblies, blah, blah, blah. Yeah. So when you have your profile and then you can relate this goes back to whatever your hypothesis is or whatever your research question is. I don't know, do you have an example of research question that you want to use for this particular case so we can know what other variables we need? Otherwise, if the research question is like the one I was giving as my example, the research question is, how likely is a piglet to develop post-winning diarrhea? So if that is the research question, what we needed was the metagenomic profile. And then over time, we will see what are the different piglets that have developed post-winning diarrhea. And then you could see that those with this particular profile, where perhaps it's missing some phyllon or is missing a certain group of microorganisms, they are the ones that are likely to develop post-winning diarrhea. If you notice that in the profile, and this has been consistently going on over time, you feed the machine with all this data. And you feed it also the outcome, that this is what they showed before the diarrhea, and this is how most of them develop diarrhea. So that when you now have a new batch of piglets, they are still not yet weaned, but you can do metagenomic and see their profile and put it into your model. Your model will tell you that based on what I have learned in the past, piglets that are looking piglets whose I don't know if that's correct in English, profile is in this particular way are likely not to develop post-winning diarrhea or are likely to develop post-winning diarrhea, and then you take your precautions in advance. So it's all about being proactive. But if you have a good example of objective or research question, we could put that in it and have an example around it.
Okay, thank you.
But
I
I'm
think that's,
not sure if I answered you specifically though. Did I?
sorry, I missed your last point.
No, have I been able to answer your question specifically? Because I thought
Yes. I think it's also more relevant to humans, especially the newborns, especially normal births and cesarean births. I think you also monitor the gut microbiomes. We can maybe predict also the immunity development or susceptibility to diseases.
yes.
I know your results were more relevant to animals, but also I think this is the case with the humans also.
That is true that the babies who were born normally and those who were born by cesarean, I think the gut microbiome has a difference, right?
Yes.
We have seen that already in previous papers, and based on that, if you feed this information into a model, and then you also feed into the model the outcome, like, okay, those babies who were born by cesarean whose gut is altered, this is how they end up reacting to treatment or reacting to a particular pathogen in the future. And then compared to the other kids that were born normally, whose microbiome were more robust, this is how they end up behaving when they face new pathogens. So if you feed the model with the birth situation, the microbiome profile, and the outcome vis-a-vis a very specific disease, then a model will be able now to learn from that experience and tell you in the future when you bring in a new baby with a new microbiome, it will be able to tell you that, okay, this baby, based on what you have given me as information on this particular baby and based on what I know, this baby is likely to be very susceptible to this particular virus if it comes in contact. So I advise you to vaccinate the baby already now.
Yeah, thank you.
Thank you very much. Let's hear the comment. Here.
Yeah. And you have to, first you have to have a research question so that you build your model to train the machine. So my question is about the sample size. For the first time you train the machine, how much do you need?
As much as you can.
Yeah.
As much as you can.
Okay.
It shouldn't be, because let me tell you, the accuracy is going to be better. If you want your model to be able to tell you good stuff, you need to train it much. And if you remember, back then when people used to do epidemiologists, used to do simulations to do prediction. They used to do Monte Carlo simulation, for example, a number of times. So this time it's not a simulation; it's the real data that you are feeding into it. So you for sure I cannot tell that this is a threshold, but I just want you to know that you need as much data as possible, and that's where it becomes a bit difficult. Because in the biological field, we are not used to having a lot of data. We are very good with obsolete, very small sample sizes. While if you go in the marketing field, people can have tons of data, like they can have on you and me alone, they have quite a lot of data on our behavior in choosing clothes, in our behavior in choosing body lotion, our behavior in what type of videos we watch. So on you, they can have, in the same variable, they can have a lot of data. In biological sciences, unfortunately, we tend to have a few variables and also very few rows per variable. So that's the challenge in biological field, and we need to improve on that if we want the machines to help us.
Okay, thank you.
Okay, thank you very much. Another question or a comment?
That's beautiful.
Hello?
Yes. There's someone online actually.
Yes.
Yeah. Hello? Yes, yes, this is, oh, sorry. This is
Yes.
Mpoki. Yes.
Right.
Yes, can you hear me? Gildas?
Yes, we can hear you.
Yes. Yes.
Okay, okay. Thank you very much for the nice presentation.
Thank you.
Although I was a bit late, but I catch up with some few presentation, and actually it was very impressive. And for me, actually, I found very interested and impressive because I'm also coming the background from the IT, the technological side.
Right.
So it's not it's not like a question, it's just a comment, adding on top of what you just presented. I think most of the African countries right now, we do have like a lot of data. We do collect these surveillance data, but at the end of the day, it's like we don't know how to deal with the data, how to make sense out of data. So with this new knowledge of like machine learning, I think learning, it's a new way to go. And for example, like here in SASD, we have this application for surveillance, if you are aware about the AFIA data.
AFIA data?
Yes, yes. I remember you also, at some point, you contributed when we were doing the cholera, the project.
I used to work with Professor Karimoribu on that.
Karimoribu, yes, yes. So actually the AFIA data, it's more into like predictive, not machine learning, but we are also thinking to go on that side.
Right.
Yes. So it's something like the young scientists. We have to pull our socks because we do have a lot of data, but to be honest, we cannot do anything. Our data, they don't make any sense. So adding on top of that, previously you showed them like you can go online, like learning from Coursera. There are a lot of platform where you can learn this kind of like machine learning. And I can tell you, this kind of like technology doesn't need you to have like a background of like IT. It doesn't.
Exactly.
And it doesn't need, yes, yeah. So I can, Dr. Gaspar, I think you're worried about like most of African countries who don't have this knowledge or capacity of to champion this, we can do this. And like as SASIs, like most of the time we're trying to see how the technology can enhance all this kind of like surveillance or doing this genomics. I think it's time now to come together, the scientists, the IT guys, to see how we can tackle this problem. And from what you presented, I think at some point we'll knock at your door.
I mean, I'm a Tanzanian.
Yes, yes, yes. We'll knock at your door because we are in the process of doing all this kind of like machine learning right now. So
I started my postgraduate journey from Tanzania, so it will always remain my back door.
Yes, so it's very nice to see someone who has a background of the genomics or this kind of the epi. Right now they have this knowledge of modeling, so it will be easier even for like when you sit together with the developers, system admins, to come up with something which will make sense out. So it's just like a comment, like, or adding on top of that, like people, they shouldn't worry about the issue of machine learning. It's something where we have to jump on. And I can tell you in the few years to come, there will be nowhere to run away from these issues of machine learning.
Thank you very much.
That's right.
And I would add that I'm not an IT guy. I'm not even a developer. I don't know how to develop a software. I'm a very good user, but I'm not a developer. So I can write my own scripts. I can write my own pipeline using other people's software. So I'm a biologist. I'm from your background. I did that same school from vet, and I mean, I'm just like everyone here. I'm not an IT guy, so you could see that these are things you can learn and do if you want to, and it all goes back to the research question. And as Mpoki says, Afia data is generating a lot of data, and it's a very powerful tool that you guys are having compared to my country, for example, in Benin, we don't have anything that powerful. And all you have to do is get that data out and then ask the appropriate question. If you have a good question, and I know Professor Mrs. is very, very good at asking the right question. And I think life is guided by the best questions, not the best answers. So if you have the best questions, you can always get a good inference out of the kind of any data that you have. It all goes to the question.
Okay, thank you very much. A comment, a question?
Kizimana, I think there was another question, I think, from Renfried.
Okay.
I think most, my name is Renfried. I'm software developer here at SACID Foundation for One Health.
Right.
Also, I'm currently a student for data science and machine learning. I'm just taking the course from Grit Learning that's a learning platform like Coursera.
Right.
So most of the question I think was already asked by the panel there. So this is just a compliment to you. I think this presentation is very, very, very nice. And there's, I think it's an open door for us also to check our platform, Afia Data, because as Mpok said, we have a lot of data, but current, the data there, the epidemiologists just come to take Excel sheet and doing analysis for this data in another platforms. So it's for us to pull our socks, to sit together, as Mpok said, and to see those kind of data, what can we predict from there, how we can help our country from those collected data, so that to predict certain diseases which we can happen at any time t. So this is a just compliment to you. This is a very nice presentation, and I think we can from this moment we can continue to communicate to see how we can help each other on area of machine learning and data science. Yeah.
And just make sure you don't just do disease prediction, because that is something that we have been doing for ages in the world. So make sure you explore other questions so it becomes more rich on how you exploit the data. So otherwise, if it's just disease prediction, of course, you can always do that. But you can, mine the data and get a lot out of it. Yeah, in many ways.
Sorry? Okay, thank you very much. Let's have the last question from the audience here in the room.
I know I'm standing between you and lunch. Right.
Okay, thank you very much for the presentation. This is Meshach from Kenya. I would like to, from your own perspective, like how far are we in using machine learning towards disease prediction and drug discovery? Is it already, probably if it's being used, maybe it's out in the West. I don't know how extensive this is, but is this? Yes, please.
Yeah. I mean, I don't know where we are when we are talking for our continent, but I know this machine learning has been in use I remember when I was doing my PhD, I had my ex who was doing medicinal chemistry, and she was already using random forest when she was doing all her docking analysis. She was working on proteins and stuff. So this is something that has been going on for a while, and that was 16, 17. So I think people are quite far, as usual, right? Look, remember, people have been using PCR for decades before we started running them locally. So it's not about how far people are, it's when can we start using it and how can we use it appropriately. That's what I would advise. That it's been there. People have been using machine learning for a while, and in different fields, both in drug discovery, outbreak prediction, disease severity, you name it, especially in cancer treatment. Here, Denmark is one of the big producers of insulin due to one big company here, and they have a lot of diabetic cases as well. So cancer and diabetics, those are the two fields that are consuming most of the machine learning brains here. It's very recent that we started using them when it comes to infectious diseases. Otherwise, for metabolic diseases, they have been in use for a while. So I think if we go back to our context, we have the brain to do it, and we have the resources, I would say, and we have the data. And it's just that we need to start asking the right questions and how much surveillance data do we need to make an inference. So I cannot tell specifically how far we are in Africa in this, but I don't think we are that neutral either. I'm sure some South Africans might have started using it because they usually start with any revolution before we join.
Okay, thank you.
Okay, thank you very much, Gildas, for your time and your willingness to share your knowledge. Professor Misinzo, can you hear us?
He's in a meeting.
Yes, thank you very much, Gildas, and all the people for a very fantastic show, very nice presentation. We are going to have a course evaluation in the end, and I think the students will like it. They are going to rank whether this was interesting or not interesting. So
I would love to see
I
that.
can already anticipate that we have you when we next offer another course. So can we put a round of applause to Gildas?
Thank you.
So asante sana Gildas, and thank you all. I turn into a Kizimana. I'm in the other Zoom.
Yeah, I would love to have the recording if you don't mind.
Yes, yes, we will share it with you.
Right. Thank you.
Okay, thank you, Gildas. I want to invite Dr. Kilaba for a vote of thanks, then we conclude this session.
You guys are so formal.
Well, thank you very much for having you with us for this very important presentation. We learned a lot from it. I think the participants now are excited and are having some ideas from which they can measure or focus after this training. And I hope it will be available to advisors whenever they are stuck. Because just excited them. Now they need a support to make things going. So this is very, very good session. Let us put 4 factorial round of applause.
Oh, you guys are fun. That is good.
Thanks.
Thank you.
Yeah, thank you very much.
Okay, thank you very much, Gildas.
Bye-bye. Kwaheri.
Yeah. Hello. Yeah. I have the image on.